So today we are looking at a demonstration of our most recent milestone for Beta AI, and that is AI-generated action spaces that are fit into further AI models. And the importance of this is that effectively the point of Beta AI is to handle problems that are generated on the fly with or without the knowledge of a given engineer. So Beta must be able to handle that. So in this demonstration, what we're doing is looking at a checkers demo where checkers has a pretty sophisticated set of rules for defining like how pieces move that is not so trivial for an AI to understand, at least directly. And traditionally this has been done through like programmers actually defining what moves are and handling all that, and AI just doesn't understand like, okay, if I choose this move, this is what the consequences are. Before I go any further, I should clarify, Beta AI is not a video game AI. It's not special to any type of problem or anything. The Beta AI currently right now is just sitting active, running in the background, and the pure system is not trained to do anything. There's a bit of a meta model which is like it's responsible for learning how to learn, but until it's invoked to solve a problem, it's kind of like no memories, no thoughts, no training whatsoever. So when I hit run to invoke the AI, the web app is telling the AI about the problem on the fly, like behind the scenes, loading in information about the given problem. And then asking for the AI's response. So, and the AI responds back to the web app that I've coded to say, okay, here's a change in the world state representation based on the problem that I've been trained to solve. And then the web app then says, okay, let me go, render that. So the only kind of like code right now I have is, how to invoke a model and there's some special code that I have that the AI runs, but it's code, I write that says, okay, this is how you render an internal state. Because otherwise, when you look at models, they kind of look like this, which is a little bit harder to understand for the average user. So when the AI actually does need to learn, like through reinforcement learning, we have a PyTorch running on the back end that has to be manually invoked. But we're trying to train the AI to learn when to use it. It actually creates information about how it learns how to solve a problem better, through a neural network or whatever algorithm it chooses, and then stores that with the world state. So this is not like traditional machine learning where you say, you create an AI model and then you solve it, and then it creates this internal set of parameters that are optimized to solve for a given problem in the world, and then that's it. That's the AI model. This is an AI that stands alone by itself and then takes in information about the world to solve a problem, and then updates some internal information in that world state that it adds in that helps it solve it in the future. So in this case, now going back onto what we're really interested in, which is this AI generated action spaces. When I say, okay, choose a move, so this is going to be the AI, I'm asking Beta AI, identify the list of possible moves that you can take in a checkers game. So we're not actually saying what's the best chess move to make. All we're saying is, okay, I've trained this model. All you have to do is just list out the moves in a reliable manner for a given player. So if I hit this, and actually, I'm supposed to go in the test manager, and then run this as choose move. So list moves. So this will actually create some internal information about the world state that's internal to the AI. And then when we go and say run this, it's gone off and run. So it doesn't actually say anything. This is something that would run behind the scenes right now. This is just test demo for me to demonstrate. And this is the data structure that it creates behind the scenes that I'm using the web app to show. So it's just creating a list of moves. So identify a piece on the board. And right now we're starting off with red. Red is at the bottom of the board, and it starts kind of from the top. So 5-1 is, but row 5 is the row where the first pieces can move. And if I go and show you what that is, this is row 5. So it's these sets of pieces that is identifying the move. And for each piece, it's given 2 possible moves: move left, move right, and forward. And we can quickly look at that. So it says from row to row, given a set of coordinates on the board, and it says okay 5-0, or it says 5-1 moves to 4-0, or 4-2, and we can check and see there's a 4-2 as well. And all of them have two moves except for one, which is 5-7, which is on the far right of the board. And as we can see, it can only have one move because it can only move to the left. It can't move right. So the AI has been trained to actually observe boundaries. That was like actually, that honestly took the most time for me to train, was identifying where boundaries are. So I'm training the AI like on very atomic basic things and then building up from those rules as I go. So if we go now, that's nice and dandy. Now there's a second model that then says take the list that's been generated um, and find out the best move. Right now it doesn't have any like fancy objectives. It's just like just pick a move. Um, it's not optimized to play for like the best moves that's what I use for tic-tac-toe for. This is just to demonstrate like, okay, you can't understand what a move is and how to pick a move. And if you look, um, it's moved the piece on the left. Um, and we can even do this again. And we can go, run back to the directive. We can run through this whole rigmarole again and, say, list the moves again. This can all be automated, so you can create like, you know, you can say, run all these actions all at once. One simulation is going to generate a new list of moves, but this time for black, so this is going to be the top of the board. I added an extra condition where I only trained the black pieces to move to the left or right. So the top, second player can only move one direction. Again, just trying to demonstrate like how this AI can handle dynamic rules constraints. And I can actually go in and change the constraints right now, and the AI will adapt because every time it gets this, it loads in the set of rules, set of constraints, set of parameters about how an action is defined, and it applies it then. So then if it applies it, comes back, and I change say the board is shrunk, it'll just handle that. You can't do that with neural networks. So yeah, if we go back, um, we go, and now we want to, pick a move again. So that'll be in the directives, get this run, and then now we can, run this, and it's, pick a move. Now the AI is a bit dumb here. If I go and do this one more time, it's not trained to jump, it's just trained to move into the direction of the closest piece. So if I do this one more time, so we do the list moves, then we do the choose moves. It's gonna, it just move. It plays like chess. I can always, train that into improvement over time. But right now, the point of this demonstration is to demonstrate. Oh yeah, the AI is both generating a list of moves to make and then taking that. So I am not, as a programmer, programming out some code to write to list out the moves, and that's a big change because in theory, the point is that Beta AI can be in the wild, and as it's talking to the user, trying to understand like what the user needs. He's just saying, okay, here's this problem. They has like, okay, what are the things you can do to address that problem? He's just like, well, I can do A, B, or C. Now the AI is defining what that action space internally is, A, B, and C, and then trying to figure out, okay, what are the consequences if I choose A? What are the consequences of B? C, the user says, okay, if I do this, I do this. And then finally, the AI is like, okay, I can calculate that B is the best option looking at this problem. And that's, that's the meat and potatoes of why I've built Beta AI. I should also point out this is not something end users would ever see. I've repeated this in I think a few of the other demonstrations. This is just a test of the pure abstract AI itself. So what we're building is Beta Guide, which uses an LLM as a front end, and that will actually be what the user interacts with. So the AI, you just talk to the LLM, like ChatGPT. We fine tune it to actually talk to our system. Our system then goes in and then handles the problem of logic, and all the large language model has to know about is how to talk to our system. This means you have to have a lot less worry about stuff like hallucinations or anything like that because we don't use large language models internally for problem solving. So we don't have some of the major drawbacks. And we also have the advantage of the fact that the AI is extremely flexible and can, adapt to changes in the problem and constraints on the dime, which you can't do with a large language model because it takes a huge amount of time and resources and effort to retrain it. So that's our demo so far. Future demos, I'm going to be focusing away less on this abstract stuff. I'm going to be focusing on like, okay, this is what an end user would see. This is why a user would want to use this in their day-to-day lives. And I might get a little bit more abstract Maybe with, I want to look at the winner tree algorithm, which is what's running this. It's a lot more mathematical. But yeah, that's the demo for today.